Quite often, the probability models of response distributions involve some parameters that are of our interest in true sense, but at the same time, some others that are really not. This second type is known as the nuisance parameters. So, usually, our objective is to eliminate those nuisance parameters from our likelihood function. But as soon as we use the full likelihood method, we are forced to incorporate those nuisance parameters along with the parameters of our interest. Now, the conditional and the marginal likelihood methods are the alternative methods used successfully to eliminate the nuisance parameters from likelihood functions. This module offers discussions on these two methods. Conditional and marginal likelihood are two popular alternative likelihood approaches where nuisance parameters can be eliminated such that likelihood function can be framed solely as a function of parameters of interest. These approaches are useful as the conventional likelihood, known also as full likelihood, can become unrealistic or fail completely when the setup is overburdened with many high dimensional nuisance parameters. We can start our discussion with conditional likelihood method. Let f of x curl under theta and lambda denote the joint density of k, where k is greater than equal to 2 random variables denoted by x1, x2, xk, and this collection is denoted by x curl. Let theta be the real or vector valued parameter of interest in the above density, that is, theta is a finite dimensional parameter of interest, and lambda be the nuisance parameter or nuisance parameter vector. If possible, suppose the joint density can be expressed as f of x curl under theta lambda equal to f of x1, x2, xr given xr plus 1 up to xk under theta into another PDF of xr plus 1 up to xk under theta and lambda, which is actually the expression where the joint PDF can be decomposed as the product of two components. The first one is conditional density and the second one is marginal density, where x curl equal to the partition of two collections, one is x1, x2, xr and another one is xr plus 1 up to xk, is so divided that conditional density becomes free from nuisance parameter lambda. Based on a random sample of size n on x curl, we have product over I from 1 to n f of x curl I under theta lambda equal to product over I from 1 to n f of x1i up to xri given xr plus 1i up to xki under theta into product over I from 1 to n f of xr plus 1i up to xki under theta and lambda. Obviously, the left hand side is nothing but the conventional or full likelihood of all the parameters theta lambda based on full data, whereas the first product in the right hand side is called the conditional likelihood function of theta given capital X, which is the data on xr plus 1 up to xk variables, and let us denote it by capital L theta given x for simplicity. In conditional likelihood method of estimation, we exclusively focus on this capital L theta given x and nowhere else, though the second product in right hand side may also carry information about theta. Thus, the conditional likelihood method may incur some loss of information about the parameter of interest theta provided theta or some components of theta in vector valued case are common in both the conditional and marginal densities. Still, very often we focus on the inference about theta from its conditional likelihood or conditional log likelihood. For example, the focus in econometric models like classical linear regression model is typically on the parameters like theta equal to beta and sigma square of the conditional density or of the conditional likelihood. Note that in this method we typically choose not to specify the form of the marginal density and only maximize the conditional likelihood or log likelihood to obtain the conditional maximum likelihood estimators of theta. Conditional maximum likelihood estimator. In the case considered above, conditional log likelihood is log of capital L theta given capital X equal to summation I from 1 to n log of PDF f at x1i up to xri given xr plus 1i up to xki under theta. Without loss of generality, assume that theta is an S component vector where S is greater than equal to 1. Then the conditional MLE is that value of theta which maximizes log of capital L theta given x or in most cases solves the system of first order conditions which are del theta of log of capital L theta given x equal to null vector, that is del theta 1 of log of L theta given x etc. del theta s of log of capital L theta given x, this vector is equal to null vector. In other words, we can say that the score vector is null where del theta of log of capital L theta denotes the score function. In this context, consider the standard regularity conditions. Let the true conditional density be denoted by f of x curl 1 given x curl 2 under theta naught, where x curl 1 is nothing but the collection of first r random variables, that is x1, x2, xr, and xr2 is the collection of the next random variables, that is xr plus 1 up to xk, and theta naught is the true parameter vector. Then the regularity conditions used for conditional MLE are capital R1, that is expectation under theta naught of del theta log of f of x curl 1 given x curl 2 under theta naught equal to null vector, or in other words the expected value of the score vector is null where expectation is taken with respect to the true conditional density. The next regularity condition is R2, which says that minus expectation under theta naught of del square del theta dash log of f of x curl 1 given x curl 2 under theta naught is equal to expectation under theta naught of the product of two terms. The first one is del theta log of f x1 curl given x2 curl under theta naught, and the second one is del theta dash of log of f of x1 curl given x2 curl under theta naught. Now it is easy to note that the second regularity condition R2 implies minus expectation of the second order derivative of capital L theta naught given x is equal to expectation of the first order derivative of capital L theta naught given x with respect to theta into first order derivative of capital L theta naught given x with respect to theta dash, and these two expectations are nothing but the two forms of getting an S cross S conditional Fisher's information matrix. In fact, the true variance matrix of the score vector, that is variance of del theta log of capital L theta naught given x, is equal to expectation under theta naught of del theta log of capital L theta naught given x into del theta log of capital L theta naught given x. Variance of del theta log of capital L theta naught given x equal to expectation of del theta log of capital L theta naught given x into del theta dash log of capital L theta naught given x, and this is nothing but the S cross S conditional Fisher's information matrix. Now consider the asymptotic properties of conditional MLE. Assuming number 1, the true conditional density f of x curl 1 given x curl 2 under theta is used to define the conditional likelihood function, which is the correct specification. Number 2, f of x curl 1 given x curl 2 under theta 1 equal to f of x curl 1 given x curl 2 under theta 2 if and only if theta 1 equal to theta 2, so that the conditional likelihood capital L theta given x has a unique maximum. Assumption number 3, 1 by n del square del theta dash log of capital L theta naught given capital X equal to 1 by n summation I from 1 to n del square del theta dash of some capital Li under theta naught given x 2 I curl converges in probability to some matrix A naught, where A naught is an S cross S non-singular matrix and capital Li theta naught given x2 curl I is actually equal to PDF f of x1 I curl given x2 I curl under theta naught. Number 4 assumption is the regularity conditions R1 and R2 hold. Now assuming the above mentioned 4 assumptions, we have theta hat CML converges to theta naught in probability, which is basically a weak consistency, where theta hat CML denotes the conditional MLE of theta, and root n theta hat CML minus theta naught converges in distribution to S variate normal with mean vector null and dispersion matrix minus A naught inverse. Obviously this is the asymptotic normality. Now we know from assumption 3 that A naught is actually expectation under theta naught of the second order derivative of capital Li function with respect to theta and theta dash for all I from 1 to n, and which is evident from Khinchin's weak law of large number. So we can say that expectation under theta naught of 1 by n, the second order derivative of log of L theta naught given x with respect to theta and theta dash is equal to A naught, or expectation of the second order derivative under theta naught equal to n times A naught. So the asymptotic distribution can also be expressed as theta hat CML minus theta naught converges in distribution to S-variate normal with mean vector null and dispersion matrix minus n times A naught matrix to the power minus 1, and this is equivalent to saying S-variate normal with mean vector null and dispersion matrix minus of expectation under theta naught of the second order derivative of log of the conditional likelihood capital L of theta naught given x inverse, and actually this dispersion matrix is nothing but the inverse of conditional information matrix. Till now what we have discussed regarding the conditional likelihood function is based on the mechanism that we are able to get a PDF f of x1 curl given x2 curl under theta, which is basically a conditional PDF, as a factor of the joint PDF. But it may not be possible always. To ensure that the conditional density will be a function of theta only, we can use the following mechanism. For simplicity, take k equal to 1, that is univariate case. Consider a random sample x1, x2, xn of size n on univariate x. This implies the joint density is now f of x1, x2, xn under theta lambda, which is equal to the product over I from 1 to n f of xi under theta lambda. Now the step 1 is get the complete sufficient statistic, say capital T lambda of the nuisance parameter lambda, where capital T lambda is a statistic based on x1, x2, xn. This implies the joint PDF f of x curl under theta lambda can now be expressed as f of x curl under theta lambda equal to f of x curl under theta given the sufficient statistic T lambda equal to small t into PDF of the sufficient statistic T lambda at the point small t under theta and lambda. Let us denote this expression by say star. Now we can write this factorization expression of the joint PDF because of the fact that the conditional PDF f of x curl under theta given T lambda equal to t is actually the joint PDF f of x curl under theta lambda divided by the PDF of T lambda at t under theta lambda. Note, as T lambda is sufficient for lambda, this implies the conditional PDF of x curl under theta given T lambda must be independent of lambda. Step 2, given the data, that is small x1, small x2, small xn on the random sample capital X1, capital X2, capital Xn, from star we get the full likelihood capital L theta under lambda given the data equal to the conditional likelihood of theta given the sufficient statistic T lambda equal to small t into some other function, say capital L star of theta lambda under t, where left hand side is as usual the full likelihood of theta and lambda as I have just said, and capital L theta given T lambda equal to small t, which is actually equal to product over I from 1 to n PDF f of xi under theta given T lambda equal to small t is the conditional likelihood of theta given T lambda equal to small t. Obviously small l of theta given T lambda equal to small t, which is actually equal to log of capital L of theta given T lambda equal to small t, is nothing but the conditional log likelihood of theta. In this context, two cases may occur. Case 1, for fixed value of theta, say theta naught, T lambda of theta naught depends on theta naught, and case 2, T lambda of theta naught equal to T lambda that is independent of theta naught for all value of theta naught. Following illustrations are useful to describe these two cases. Illustration 1. Let x1, x2, xn be IID normal mu sigma square variable. Let sigma square is the parameter of interest and mu is the nuisance parameter. Now the joint PDF is here 1 by root over 2 pi sigma square to the power n e to the power minus 1 by 2 sigma square times summation I from 1 to n xi minus mu whole square. If capital T sigma square equal to summation I from 1 to n xi square and capital T mu equal to summation I from 1 to n xi square be two statistics, then we know that T mu and T sigma square is jointly complete sufficient for mu sigma square. This implies given sigma square equal to some fixed value, say sigma naught square, T mu equal to summation xi is sufficient for mu only. Also the statistic T mu does not depend on sigma naught square, that is it is independent of sigma square for all sigma. This implies the present illustration is in favor of case 2. Now the conditional PDF of f of x curl under sigma square given the sufficient statistic T mu equal to small t is equal to joint PDF of x curl under sigma square mu divided by PDF of the statistic T mu at the point small t, where small t is a realization of the statistic T mu for the sample realization x curl, and that is equal to summation small xi, and that is nothing but n times small x bar, where small x bar is the sample mean. It can be shown that on simplification we finally get this conditional PDF of x curl under sigma square given the sufficient statistic T mu equal to small t can be expressed as some c sigma square, that is a function of sigma square alone, into e to the power minus 1 by 2 sigma square times summation I from 1 to n xi minus x bar whole square, and this is denoted by capital L of sigma square given T mu equal to small t, which is nothing but the conditional likelihood of sigma square given that the statistic T mu equal to small t, and as I have already said that small t equal to n into x bar. Or we can say that the log conditional likelihood small l of sigma square given T mu equal to small t is equal to log of the function c sigma square minus summation xi minus x bar square by 2 sigma square, and obviously it is a dependent function of sigma square only, and this implies we can conduct statistical inference for sigma square based on the above conditional log likelihood. Now consider the next illustration. Illustration 2. Let x1 follows normal with mean mu1 and variance 1, and similarly x2 follows normal with mean mu2 and variance 1 independently. Let theta equal to mu2 by mu1 is here the parameter of our interest, and lambda equal to mu2 is the nuisance parameter, that is mu1 equal to lambda by theta. Now it can be derived that for fixed theta equal to theta naught, the sufficient statistic for lambda is T lambda under theta naught equal to capital X1 plus theta naught times x2, which follows normal distribution with mean mu1 plus theta naught times mu2 and variance 1 plus theta naught square. Here the sufficient statistic T lambda and its distribution depends on the fixed value of theta, that is theta naught. So clearly this illustration indicates case 1. It can be shown that the conditional log likelihood small l of theta and theta naught given T lambda under theta naught equal to small t is independent of lambda, and which should be the case actually. This implies we can make statistical inference for theta based on this conditional log likelihood function. For example, to find conditional maximum likelihood estimate, we can solve the equation del theta of small l of theta theta naught given t lambda theta naught equal to small t at theta naught equal to theta equal to 0, and this implies on simplification theta hat equal to x2 by x1, which is actually intuitively a sensible estimate. As a brief outline of marginal likelihood, which is also known as integrated likelihood, we can say that in the context of multi-parameter, this likelihood is obtained by marginalizing or averaging out some nuisance parameters from the full likelihood model and retaining the parameter or parameters of our interest. In reference with Bayesian statistics, this may be called as the evidence or model evidence. Maintaining the previous notational implication, let the nuisance parameter lambda follow the density denoted by P of lambda under theta. This implies the PDF f of x under theta can now be obtained as integration of the PDF of x under theta lambda multiplied by the PDF P of lambda under theta into d lambda. Now, based on a sample x1, x2, xn denoted by say x curl, thus the marginal likelihood of theta will be capital L theta given x curl equal to integration of joint PDF f of x curl under theta lambda into PDF P of lambda under theta, where integration is done with respect to lambda. Note that marginal likelihoods are actually difficult to compute and the particular solutions are available for marginal likelihoods for a small class of distributions. Otherwise, that is, for all the other cases of marginal likelihoods, numerical methods are applicable. In this module, we have studied some approaches to apply conditional likelihood method to eliminate nuisance parameters from the likelihood function. Also, a brief discussion is made on the application of marginal likelihood method for the same purpose.